Okay. Today, combined with yesterday, we're talking about the wave nature of light. Before this, when we talked about light, we were talking about the ray model of light. That is, we were treating light as stuff that just goes in a straight line, and then when it hits something, it can either refract or reflect. But now we're actually looking at the wave nature. Now, we did introduce Huygens' principle when we started talking about the ray model to describe why the ray model works. But now we're looking at things that only can happen if we have a wave. So in class yesterday, we talked about the thin film interference. That can only happen if you have a wave. That's light is a wave. So here, my introduction slide, I have a picture reminding us that light is an electromagnetic wave. It has electric and magnetic fields that oscillate. And so if I have light that's going from the screen up here back to Toussaint in the back of the classroom, there are electric fields that are oscillating as the light is traveling back to Toussaint. And there are magnetic fields that are oscillating as the light is going back to Toussaint. And so you have those two things oscillating mutually perpendicular to the direction of the velocity. And of course you have the directions that, while it is not a true equation that E cross B is equal to C, right, because you have the wrong units, the wrong numbers, in terms of using the right-hand rule, you can remember that way. When I was grading somebody's exam, to give it the proper units, I wrote, E cross B divided by magnetic field squared is equal to V. That is a correct equation. So you can keep those directions straight. Chad, your car's on the floor here, I think. All right, can't even tell if it's yours. It might be somebody else. I just don't want to bend over. So the first thing we're going to talk about today is going to be, I believe, I hope my memory's correct, talking about polarization of light, and then we'll get back to talking about interference effects. So what is polarization? When I talked about that light going back to Toussaint, I could talk about the direction the electric fields are oscillating, or equivalently the direction the magnetic fields are oscillating. Because of that fixed relationship between the electric field direction and the magnetic field direction, I can talk about either one. Whose is it? It's Lauren Lee. Wow. Okay. So I can talk about either electric fields or magnetic fields. And just by sheer convention, we talk about electric fields. It doesn't matter. It doesn't change any discussions, really. But we just choose to talk about electric fields. So for the light going from the screen to Toussaint, the electric fields could be oscillating in a vertical direction, as they can be going like this, because that's perpendicular to the velocity. But they can also be oscillating like this. That's also perpendicular to the velocity. And so there's a whole 360 degrees worth of directions the electric field could be oscillating. Actually, if you think about it, since it's going up and down, it's really only 180 degrees. Because after you've gone halfway through the circle, you're just saying the opposite side is positive. But you can have the electric field oscillating anything in that circle. And polarization deals with the orientation of the electric field oscillations as the wave is propagating. So right now, the light that's coming from the screen is randomly polarized. That means that we have just as much light with electric fields going like this as we have light with electric fields going like this, as we have light with electric fields going like this, and now I have to bend over. You see that incredible flexibility? And so we have unpolarized light. Electric fields oriented in all of those 360 degrees, it's obviously continuous, that are perpendicular to the direction from the screen to Toussaint. Now, if I use a polarizer, here's a polarizer, what it does is it restricts the direction that the electric fields can oscillate. That is, if I put this polarizer up here, now the electric fields can only oscillate in the vertical direction because this blocks everything that's horizontal. And if I rotate it, I change the direction I'm blocking. Do you see any changes? No, you don't. Because the light is uniformly distributed, you have just as much in all of the different directions. Now, if I take 2, go like this, you do see a difference depending on the orientation with the second one. Because the first one sets the direction of the electric field. Then the second one, which we call an analyzer when we put a second one there, it's going to only let some of that light through. So polarizers are dealing with the direction the electric field is oscillating. And everything we're going to talk about here is plain polarized. I have some of those 3D glasses you use when you go to the movies. When you watch the 3D movies and you get those cool glasses, one of the weirdest things you can do is go to the bathroom and wash your hands and look at yourself in the mirror. Now go in the bathroom and wash your hands, those are not weird. It's the looking at yourself in the mirror that is weird. Because you'll look and you'll see your eyes do funny things. Anybody ever done that? I've got like 15 pair of glasses, so if you want to play with them after I finish my hour and a half talk, 2-hour talk, you can do it, and it's kind of fun. Don't look so scared, Michaela. What they're using there is what we call circularly polarized light, which is a little more complicated than what we're going to talk about here in class today. So let's get into this a little bit. I've already said everything that's on that slide, so I don't have to stop there. Anybody know where I put that little stylus I was carrying around and dropped? Certainly not in my pockets. Excellent, there it is. Can't write very well without having my writing tool. Okay, so first thing. Let us suppose that I have unpolarized light and then I put a polarizer in front of it. If it's unpolarized light, that means that you have light equally distributed in all directions. When you put the polarizer in front of it, it blocks one half of it. With some very simple calculus, you can show that that's the case. But the first rule with polarizers is unpolarized light, you put a polarizer between. And if it's an ideal polarizer, of course ideal doesn't exist, but if it's an ideal polarizer, that means that it's perfectly transparent and it perfectly blocks all of the light except for the light that's oriented in its direction. Then it will block half of the light. Once you have polarized light, then things get a little more interesting. So here we have a picture of electric field. Why electric field? Because light's an electromagnetic wave. If we're going to do calculations with light, we need to go to either the electric field or the magnetic field. So I have light that has an electric field as indicated by that bold green vector. And the light goes through a polarizer, and the polarizer is only going to allow electric fields parallel to my arrow through. And so I look at that vector, and we learned in the first 2 weeks of the first semester, that we can take a vector and we can resolve it into its components. So if you look at that picture, how much of the total electric field is parallel to the transmission axis? That is the PX component. How much of the total? Okay. E cosine of theta, where theta was the angle between the orientation of my electric field and the orientation of the transmission axis. How did she get that? Because the EX was the adjacent side of the triangle and E was the hypotenuse. And cosine theta is adjacent over hypotenuse. So the electric field that's allowed through my polarizer is going to be the total electric field times cosine of the angle between the polarization direction and the transmission axis. Well, how does that tell me anything useful? Right? That's telling us about electric fields, and really nobody says, hey, this light has an electric field of 5, whatever units, right? You don't do that. But you do say, this light is bright, this light is brighter. And you can get a little device to measure how bright the light is. You're not measuring the electric field strength, you're measuring how bright the light is. So what we want to do is to go from this and relate it to what we measure and see. And what we measure and see is the intensity. That is the power per unit area. And it turns out that the intensity is proportional to the electric field squared. So that means that if I square the equation I have at the top for electric field that's allowed through is proportional to the intensity that's allowed through, and the electric field that I started with is proportional to the intensity I started with. So taking the equation I have at the top of the screen, obviously you can't see it now, then using those I forgot a square. Using those definitions, I can square this and say EX squared is equal to E squared cosine squared theta, and then because they're proportional and the constant proportionality will be the same, that gives me the intensity transmitted is equal to the initial intensity times cosine squared of that angle. Again, theta is the angle between what two objects? What two objects is theta the angle between? Okay, the transmission axis and the polarization direction of the light. This equation that I have in a box is called the law of Malus. And of course, it's on my next screen. Okay, not the next one. On one's coming up after this. Somewhere. I've already talked about, I've gone pretty quickly through a lot of stuff. There's our first indication of the law of Malus, and the next screen is the one that has it drawn out. I'm going to stay on this before I move to the next one to talk about how a polarizer is made real quickly. If you look at the picture is everything we can understand. We have a microwave transmitter that's just a dipole antenna. That is, we're going to have an antenna, and this side will be positive charge, and this side will be negative charge. If this side's positive, and this side's negative, that makes an electric field. What direction is it going to point? From blank to blank. From positive to negative. So the electric field, the way I first indicated, would be pointing like this. But that transmitter is, of course, changing the charges back and forth, so the electric field is going to oscillate in these directions. So in that picture, our electric field is oscillating horizontally. So this dipole antenna creates a polarized wave. Polarized because the electric field is oscillating in just one direction. Now it comes to that metal, that's metal, so it's conducting. When it hits that, I have electric field. What happens in a metal, a conductive material, when there's an electric field present? Well, the very first thing, it's a conductor, so I have electrons that are relatively free to move. So what happens? The electrons what? The electrons begin to move because there's a force. Force equals QE, right? So the electrons begin to move. But what direction will they move with that electric field? If the electric field is horizontal, what direction is the force going to be to the electric field? Horizontal. So the electrons want to move horizontally, but we have vertical slits that don't allow electrons to move very much horizontally. As a result, you can't absorb much energy horizontally. So the horizontal light, or electromagnetic waves, goes through because it can't absorb that because the electrons can't move. In the vertical direction, you don't have, the electrons can move up and down pretty freely, there's nothing to stop them, and so it'll absorb radiation in the vertical direction. So this polarizer has a transmission axis that's horizontal. It seems wrong because that's perpendicular to the slits, but you have to understand why it's allowing the waves through and blocking waves. So in that case, waves just go right through because I have horizontal polarized waves, and I had a polarizer set with this transmission horizontal. They went right through. Nothing stopped if it's an ideal polarizer. Obviously, not even this would be ideal because you do have the electrons to move a little bit, which means they could absorb a little energy. Now, if I look at the second picture, now the electrons are free to oscillate horizontally. It's going to absorb the horizontally polarized electromagnetic radiation, and it stops it. Nothing comes through. Is that much clearer? Now the third case, I have some angle theta between what two axes? The transmission axis and the polarization axis. The polarization axis is the axis of the polarized light or waves. Transmission is the axis that allow through, and we have that law of Malus to tell us how much we'll get through. So here is the first slide that calls it, oh no, it's not here either. This is what happens if you have unpolarized light hits a polarizer. Unpolarized light, cut half of it out. Come on, law of Malus slide. Nope. I'm going to show you demonstrations as soon as I get past this. Okay, here's our law of Malus slide. Notice it's not, malice aforethought. The intensity that's transmitted is I0 cosine squared. Remember, it has cosine squared because we had to square the electric field. The electric field transmitted had cosine theta in it. So it's pretty simple. Now, let's do some demonstrations before I forget. So I've got things set up here, or at least I did a while back when I was setting up, surprisingly enough. Come on, faster. Sorry, I have to change one thing. Okay, so now I just have a piece of paper here, and I'm going to put a polarizer down. I'm going to turn off all the lights because the room lights cause some issues here. So I have light going through a polarizer. Now if you compare where the polarizer is to where it isn't, you can say, okay, it's blocking some light. Should it be blocking some light? Yes. How much? Half of it. Why half? Unpolarized. Now, just to check that, I can rotate it. If I rotate it and the light is polarized, I should see some changes. So I rotate it. Good, no changes. Now I'm going to put a second polarizer on there. Did that block some light? Yes. Yes. Ideally, because I have the polarizer aligned with the direction of the polarization of the first one, ideally it should have blocked nothing. So you can see here, hey, those aren't ideal, right? It's blocking some light just because it exists. But now let's rotate the orientation. Yeah, and so you see, aha, when you get to 90 degrees, what's cosine of 90 degrees? 0, yeah. Had to be one or the other. So cosine of 90 degrees is 0. That means when you have 90 degrees between your polarization axis and your transmission axis, it should block all the light. Now I'm going to add something in between. Put a second polarizer. What's the orientation between the first polarizer and the second polarizer? 90 degrees. How'd you know that, Sally? Because it's 90 degrees, it's blocking all the light. Oh, goodness. Okay, I got to start the camera again. It times out. There's different cameras with different functions. Apparently that's the function that times out. Okay, now I still have this other polarizer in between. I'm going to rotate it. What kind of crazy magic is that?
So is the bottom one and the top one and then in the same direction?
The bottom one and the top one are perpendicular to each other, so they block everything. The middle one is now at a 45-degree angle. If I have the bottom one, how much does the bottom one block? Half. Then I have the middle one at a 45-degree angle. A 45-degree angle, cosine squared of 45 is 1/2. So how much should that middle one block? Half again. So I should have 1/4 of the initial intensity when I go through those two. And then I have the top one. What's the angle between the polarization coming out of the middle polarizer and the top one? 45 degrees. But if it's at a 45-degree angle, how much does it block? Half. So I just go from 1/4 to 1/8. So the intensity of the light that's coming through here is 1/8 of the initial intensity, whereas the intensity out here should be 0. Now, why is that interesting or important? Well, first of all, it's not what you expected, is it? And second of all, it's a fundamental concept for quantum mechanics. When you make a measurement, that measurement will change the system. And so when I put this second polarizer in, what we call an analyzer, that analyzer changed the orientation of light. The light, after the first polarizer, was all, let's say, vertical. And so if I put a horizontal polarizer, it would have blocked it all. But when I put that intermediate one in, it said, okay, the vertical had a portion that was 45 degrees from vertical. And then we get to the third one. I do have another camera, and somehow I got my default set. I'm sorry about that. I will figure out how to change it after class, of course. When I get to the third one, because the second one was there, it changed the amount of light that comes through. Now, let's look at some other cool things. So I have here the letter R. Why? Because it's, of course, my initial. And on that letter R, I'm going to put a calcite crystal. Everybody's played with calcite crystals, probably? Maybe? Anybody know what's going to happen when I put the calcite crystal on it? No? Okay. What do you see? I have a double image. And if I rotate this, one of them stays put and the other one moves. Trying to do this in mirrors. Okay, let's just do it this way and I won't screw up. The one that stays put, we call the ordinary axis. The one that is moving, we call the extraordinary axis. Now I'm going to put a polarizer on top. What do you think is going to happen? Does it block half the light? That was a very good answer, whoever said that. Lindsay. She's all, yeah, I'm going to take credit for that. Okay, so it blocks half the light. What do you see happen to the R? One of them disappeared. Now if I rotate the polarizer, what happened? It switched which R it was. Now, based on this, we have something interesting observed. Let's come up with a hypothesis. Why would that have occurred?
My hypothesis would be that the R's are due to light that is polarized differently, and so we have one way it's letting one of those things of light spectrum, and switch the other way it's letting the other polarized spectrum.
Okay, now we're not going to go through the whole, come up with the test and so on, but she's absolutely right. We have thank you. We have two different speeds of light depending on the polarization angle. And so just by changing the polarization that we're selecting, we have a different speed of light. And because we have a different speed of light, we have a different amount of refraction that occurs. And thus, we have the two R's. Now, you think that's, okay, I think you should think that's cool. If you don't, then I just disagree with you. Here's my next to last, well, it's my last trick, but it's a trick in 3 parts. So here is a glass slide that somebody put a bunch of tape on. Why did they put the tape on? Not because they were crazy or bored, because tape will actually rotate the polarization of light. Some of you people may have done organic chemistry experiments where you actually measure polarization rotation in chemicals. No? Well, tape is something that will rotate the polarization. So that means when light that's polarized, notice I put a polarizer underneath, when that light goes through, the orientation of the polarization rotates. And for different colors, you have different wavelengths, and it turns out you rotate different amounts for the different colors. So putting a second polarizer on top, I'm blocking light that was rotated by, well, in this case, I'm blocking light that wasn't rotated and allowing through light that was rotated by 9 degrees. And of course, I'm going to allow some light that was rotated at the other angles. So if I rotate the top polarizer, what's going to happen? That's cool, right? I don't know. No, that's awesomely cool. I don't know is not the answer.
The question is, what kind of tape is it?
Oh, I think it's a standard tape, just, Scotch tape. Now, for those of you who are old school Unionites, really have to change back to the other one. I think this is the default app, in case you care. Anybody recognize? Oh, got to turn it the other direction because of the reversal. Anybody recognize this? Lindsay? Okay. This is a student-made rendition of the old clock tower that used to be here at Union College. Why student-made? Because nobody's got time for that except for students. I put a polarizer on top. Okay. I started with the wrong orientation. How do I know that's wrong? Well, because the moon's not supposed to be blue. The sky's not supposed to be white. So I just rotate 90 degrees, and there we go. Dark sky, white moon, and a pretty clock tower. Now, these are all random colors. This one here, God help the person who had the patience to do this. You probably recognize this symbol. I am not even going to say anything in response to that. Put the polarizer on top. Pretty standard U.S. flag, right? Clearly not. So let's try rotating. Is that not awesome? Obviously, this was not made recently because it has 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6, 7, 8. 6 times 8 is 48. So this was made, prior to 1949, when there were only 48 states in the Union instead of 50, or by somebody who didn't pay attention, because that happens as well. Okay, so those are my demonstrations on polarization. Now, one of the two things you have to do in lab today, oh, come on, get out of there. One of the two things you have to do in lab today is to test the law of malice. And so your kits, which are in the back room right now, your kits have 2 polarizers, a light source, and a light intensity measuring device. So you can measure the light intensity and rotate the polarizations. So I'm not telling you how to test it. The test is pretty darn obvious, but I'm not telling you how to do it. I want you to think about how to test the law of malice. Any questions about that first part? Who knows what the law of malice is? That, okay, good. Yes. Making sure, we're all here together. Problem-solving strategies for homework problems that might deal with polarization. First, if you have unpolarized light and you have a polarizer, half of it gets through. And of course, after coming through the polarizer, it's polarized parallel to the transmission axis of the polarizer. If you have polarized light that hits, by the way, get out your clickers because the next thing is a clicker question. If you have polarized light that hits another polarizer, then you need to determine what the angle between the transmission axis and the polarization axis is and use the law of malice. So, now for the... I have 2 examples here that I'm actually... Well, let's go through them. It'll help you on the clicker question. I have initially randomly polarized light. It goes through a polarizer. What's the intensity that gets past that first polarizer? 1/2 of the original intensity. So I have I1 is equal to 1/2 I0. So when I'm going through a problem like this, I write down I1 equals 1/2 I0. And then I have a second polarizer that's oriented 30 degrees from the first polarizer. How much gets through that? Okay, I'm just going to go from I1. So I1 cosine squared of 30 degrees. Anybody know what cosine squared of 30 degrees is? This is one of the things I had to memorize in high school. That's why I'm asking. Apparently not. Cosine squared of 30 degrees is 3/4.
How do you do that?
How do you do what?
Like on the calculator.
How do you get cosine squared 30? On the calculator, you put in cosine 30, and then after you have the number, hit square. They don't have a cosine squared button. So now I have I2 in terms of I1 and I1 in terms of I0, and then I put them together. Why do I do it sequentially like that? Because sometimes you have a problem. I mean, test problems, you got to make sure the students understand. You might have 4 polarizers. You'll get confused if you keep trying to go through. So just do each one separately and then do your answer. So I would have, in this case, I2 is equal to 1/2 I0 times 3/4. So 3/8 I0. So the intensity should be 3/8 of the incident intensity. It really is pretty simple doing these problems, isn't it? Especially considering what we've been doing in the past. So let's look at, I believe I have a second one. Nope, I have the clicker question right next. So what is the intensity of initially unpolarized light of intensity I0 that goes through 3 polarizers, each oriented 45 degrees clockwise from the previous? So I have unpolarized light. What? And then I have 3 polarizers. Whoops. That was bad. Let's undo that. With polarization angles that vary by 45 degrees. So this one is vertical.
Okay. I knew that thing, but yeah, that's right.
Okay, still waiting on 4 people. She's working on it, right? It didn't take us, Sally. But we're waiting for you, Sally. But at this point, put an answer in so we can go on. You may not have had your final answer, but you know where you're going. Are you on the wrong channel? There we go. Okay. We had 0, 0, 2, 16, 0. That's good. The distractor here that I'm checking for is to make sure people didn't answer E. Because you have 9 degrees between the first polarizer and the last, if you didn't understand what went on over here, you might have said, 9 degrees is 0. But it's not, because the middle polarizer reset the orientation. So how much did the first polarizer block? Half. So we have I1 equals 1/2 I0. How much does the second polarizer block? It's 1/2 again. Now, for those who don't understand why it's 1/2, cosine squared of 45 degrees is 1/2. And finally, how much does the last one do? And so then you just put them all together. I3 is equal to 1/2 of 1/2 of 1/2 I0 equals 1/8 I0. And really with polarizers, it doesn't really get much more complicated than that, except for, you might have different angles instead of all of them being the same. Any questions about the polarizers? Because I think I'm done with those. Okay. Please be done. Oh, I do have some applications. This display right here is a liquid crystal display. A liquid crystal display runs on the principles of polarization. What's special about these liquid crystals? When you shine light through, the polarization of the light rotates based on the voltage you put across this liquid crystal material. So you can adjust the rotation of polarization by simply putting different voltages. So the basic LCD display, you put a polarizer up, so you have your first polarizer, and then you put a liquid crystal in between, and then you put a second polarizer. And that liquid crystal can either rotate it or not rotate the polarization of light. So it can be 0 degrees or 90 degrees depending on the voltage you put, or somewhere in between. And so you just adjust the voltages, and what comes through depends on what voltage you put on there. And so the LCD is a very simple application of polarization. And so that means that if you take a polarizer and you put it over an LCD display, you'll see variations in it. Now, displays like this, they're so compact as the pixels are so close together, it's hard to see much, but there are variations that you will see if you just put the polarizer over and rotate it, because it's got the polarizers in there to make the picture. This display is a much simpler display. It will be much clearer what's going on if you use the polarizer there. Unfortunately, this one doesn't have a battery. It needs light to work, and if you put the polarizer on, you're probably going to block the light unless you're really careful. So there's an example of using polarization. Another example is in the sky. You know I'm a nerd, right? I teach physics. It's what I'm born to do. One of the things that just gives me the grins is on a bright sunny day wearing polarized sunglasses, driving down the road going... You guys ever try that? No! Now, first of all, you have to have polarizing sunglasses. If you don't have polarizing sunglasses, well, then it's not going to do anything fun for you. But when light reflects off of the road, the light coming from the sky is generally randomly polarized. But when it reflects off of the road, the reflected light is going to be polarized parallel to the road. And so the reason they have polarized sunglasses for snow skiing or being at a lake or ocean is so you can have a polarizer that will block the horizontal light. It blocks half of the general light, but all of the light, or most of the light, is reflected off of surfaces. So you cut the glare by having those polarizers. So when I'm driving down the road, it's a bright sunny day, and I have sunlight reflecting off the road ahead of me, as I rotate my head, the road gets brighter and darker because I'm cutting the glare or allowing the glare through. I think that's really cool. It's even better like you go out on Holmes Lake or something, you got the sun reflecting off the lake, and you go like this, and it disappears, appears. It's really awesome. Also the sky. Okay, don't laugh. The sky. We know now why the sky is blue. Why is the sky blue? Is it what? Philosophical question. No, it's not. We do not deal with philosophy. No. We talked about this in class. We had to click a question on it.
Gases in the atmosphere?
It's because of the radially scattering from the gases in the atmosphere. The light is absorbed and then re-emitted. And the radially scattering is much more efficient at scattering blue light than it is at red light, so the sky looks generally blue. But that scattering process involves polarization. So let me go forward to a slide to indicate that polarization. So I have the sunlight, light coming from the sun is just randomly polarized. if you look directly at the sun, the light you see coming directly from the sun didn't get scattered. You just see, randomly polarized light if you look directly at the sun. But if you were off at some angle, the sunlight made the molecules or electrons in the molecules oscillate. And those oscillations could only be in the direction of the electric field, so perpendicular to the velocity. So if you look at this person that's here, they're looking up, so the sunlight was going parallel to them, and then the scattering occurred, and you have no scattering in the vertical in this direction because the electric fields had to be perpendicular to the direction that was propagating. So right there is no electric field oscillation like that because that would be parallel to the velocity. And thus, the molecules that are absorbing and scattering the light aren't going to give you any motion in that direction. So this person down here sees all of the light polarized in the direction perpendicular to the propagation because they're looking at a right angle to the original propagation direction. And so if you're looking at that perfect angle where the sunlight goes like this, hits the atmosphere, and then comes to you at a right angle, it's completely polarized. Now, of course, it's impossible to look at perfectly that direction because the sunlight could hit upper atmosphere or lower atmosphere, and only one of those is going to be perfectly polarized. Goodness gracious, great balls of fire. Let's just take a break right here, and then we'll talk about our next topic, because this is actually in the break between topics.